Okay. Hello. So we're actually done with 2.4 and excuse me. Now we can move to section 2.5. Here are the homework problems for the section. I listed them here. They will not be due with the homework notebook on Friday. However, 2.5 will be included on your exam. So you definitely should take a look at these problems and attempt to do these problems before your exam next week. Okay, so this section, we're still talking about induction. It's just a different form. This first principle is the principle of complete induction. And of course, the presenters talked about that today. I think the last group talked about PCI today. So the difference here is that you're supposing S is still a subset of the naturals with the property for all naturals, so for all n's belonging to the natural numbers, if the some set 1, 2, 3, all the way up to n minus 1, if that's a subset of S, then n belongs to S. And if that's true, then you could say therefore S equals n. So notice here there isn't a base step, although, and you can read, so a base step isn't required for the PCI, although it's highly recommended. You can read the book in section 2.5 to where they discuss why it's not needed. But I would say to err on the side of caution and just always do the base step. It only takes a couple seconds. It's a quick check, and yeah, so you won't confuse yourself to say, oh, with PMI, I need a base step. With PCI, I don't. Just to avoid confusion, just always do the base step. Okay. Okay, so I've actually written the first question for your quiz, and it's prove using the PCI for all n natural numbers. N belongs to the natural number. 1 plus 3 plus 5 plus dot 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 plus 2 to the n minus 1. I'm sorry, 2 times n minus 1 equals n squared. And we actually proved this with PMI, if you recall. And this is also in your book. So the difference here is, one, I want to make sure you understand it. Your book doesn't clearly state where they use inductive steps, so I want to make sure you include that in your proof. And I actually want to see your show part for this. So I want to see your show part. I will actually be grading your show part for this because I want to make sure you're not just copying it from the book and you actually understanding what you need to show and everything. So that's the first problem. And of course, within this video and probably one more, hopefully one more, I'll have the other questions. And I'm not for sure how many questions we're going to have yet, so I'll let you know that too. I'm trying to go for 5, but we'll see. Okay, so we're actually going to do a proof together, and this is also one in your book as well, but they sort of put it all together in a paragraph format, so I want to kind of list it how we usually do these types of proofs, and hopefully this will make sense to you all. And the proof is proof for all n, so for all n belonging to the naturals, and n greater than or equal to 1, n has a prime factor. Okay, so remember, I always say that when you're doing proofs, you should make sure you understand what this proof is asking. So think about what that means. So it's saying any natural number greater than 1 has a prime factor. Okay, well, 2 is prime, so 2 is its own prime factor, right? 3 is prime, so there's its factor. Let's think of another. 9. 9 isn't prime, but we can factor, always think about multiplication. We can break 9 into 3 times 3. So there's a prime factor, 12, 3 times 4, 16, 2 times 8. And in fact, I believe there's another proof, and I don't know if I had you guys prove this, but it might be a great exam question if you're listening. I don't know. It depends on how long the proof is, but every even natural number, 2 will be its prime factor. I think that's a proof somewhere. So you might want to look for that. Okay, just a side note. All right, so we're going to prove this using the principle complete induction, so PCI. Okay, so I might be repeating myself because I paused for a minute and I'm not for sure if I started this, but again, I would suggest you stop the video and then write everything down and go back to it. Okay, so we're trying to prove, yes, I think I had just stopped at understanding what the proof was, okay? So now, starting our proof, we're going to let S be a set that's equal to, S equals to n belonging to the naturals, such that n is greater than 1 and n has a prime factor. And then for our base step, well, we sort of look and see what's our first element, right? It wasn't given to us, but we know what our first element is because of how our conditions were set. So we know the first element in S equals 2. Well, 2 is greater than 1, and 2 has a prime factor, i.e. 2, right? So 2 belongs to S, and we just proved the base step. So again, like I said in class, the base step is pretty straightforward. You shouldn't have too much trouble proving the base step. You're just looking at the first integer. In case if you're doing recursive type of definition, like what the presenters did, they had to look at the first 2 terms, but it should be clear from your proof what your base step is. What's your first number? First or second numbers, depending if you need to do more than one. Okay, so the inductive part, which is the main part, the heart of our proof, we're going to let m belong to the naturals and let m be greater than 1, okay? So our goal is to show that m has a prime factor, right? And so we suppose k belongs to the set 2, 3, ... to some m minus 1, because remember we're doing PCI. So we're supposing up until m minus 1 and not up until m. And we know that that's a subset of S. That's just by the definition of PCI. You can go back and look at your notes on that. So we have to show that M belongs to S. Okay, that's what we need to show. Well, we actually have to think about cases, because we have to think of a case where basically we need to think of, when we think of numbers, they're either prime or composite, and we're talking about integers, right? And so we have to say it, but we can't directly say that, right? So case 1 is, well, suppose M has no factors besides 1 and M. Well, that's what it means to be a prime number, right? So by definition, that's what it means. You don't have to say by definition, that's what it means to be a prime number. I mean, I always say put more in proof than less. So if you want to put it in, that's fine. But once we say, well, suppose M has no factors besides 1 in itself, right? Thus, M is prime, and hence M belongs to S because it's its own prime factor, okay, like 2, okay? So that's the first case. So we're done with that case. Now we have to get a little deeper, okay? So case 2 is, we're supposing M has a factor other than 1 and M, okay? Thus, M is composite, okay? So there exists a factor X, where X is between 1 and M, right? Hence, X belongs to S, okay? Thus, X has a prime factor, and this is by the inductive step, okay? And you can go back and look at our inductive step to make sure that makes sense, okay? And so, hence, this prime factor of X is also a prime factor of M, okay? We didn't talk about any type of uniqueness. If it was talking in terms of uniqueness, then we would have to do some more work to show that there's a unique prime factor, if that's true, and I'm not for sure if that's true, okay? And so thus, M belongs to S. So therefore, S equals the naturals, and every natural number greater than 1, I could have put N, but we can simplify that, has a prime factor, and that deserved a QED, okay? So again, you can go back over the proof, go back over my steps if something wasn't clear. Okay, so your second question for your proof, for your quiz, use the PCI to prove for all n belonging to the naturals and n greater than 22, n is equal to 3s plus 4t for some s and t belonging to the integers, and x is greater than or equal to 3 and t is greater than or equal to 2. Okay, so again, my suggestion is to really think about what this proof is asking. Try some examples, and then see if you can formulate using the PCI for this, okay? My hint to you is that I found this problem in the book, okay? That's my hint to you, okay? All right, so moving on. I think I'm going to start the next video, so this is the end of that, and then there's one more main principle in this section that I want to talk about. There are some other theorems that you need to know, especially for those who are math majors and going forward. in the math sequence, you definitely need to know some theorems, but it's one more main principle that I want to talk about.